Okay, so let's figure out how to compute the initial price level or restrict it or not. Divorce ourselves from the Gale diagram and of course we can't completely, but we'll push it into the background and we'll attack this the way Samuelson did. So here's what we're going to do is we're going to solve the household problem, the consumer problem, for saving function. So we're going to write the saving function as it's going to be a key thing. YII minus the endowment minus CII, that's what you save, and that's going to be a function. It's going to depend on your preferences. It's going to depend on the rate of return and your endowments. There's going to be some function. And then we can write our equilibrium conditions. Can be written compactly like this: M over PI or PT is going to be S, and alpha I is just PI plus 1 over PI, and then we have our endowments there implicitly. So this is going to be a first order difference equation in PI. I goes from I greater than or equal to 1. That's how we're going to treat this. So we're going to write down some preferences for which we can calculate the saving function easily, so that we can get somewhere by solving this by hand. So let's proceed that way. We're going to the way to read this equation before we do this is the left-hand side. That's the dis-saving of the old generation at time I, and the right-hand side is the saving of the young at time I. So what's going on is the old are sending money this way to the young, the old to the young, and in return, the young are sending, what are they sending? They're sending YII minus CII. They're sending goods. They're sending goods to the old. This is the way this goes. And so this is what this equation says. You know, the old are, once you become old, you just put all of your money, use all of your money that you have to purchase goods. When you're young, your demand depends on the rate of return on money, which is going to be given by this alpha I that we computed. Again, to remind ourselves, alpha I was the gross. It's a reciprocal of the gross return on money. It's the inflation rate. So here's something fun to work out. Suppose that u of c is equal to log of c. Then a simple calculation will show that the and so let me write preferences. I'm going to write yii comma yii plus 1. I'm going to write that as your endowment when you're young and your endowment when you're old. Just write that like. And you're going to see I'm going to impose that W2 is less than W1. We're going to see consequences if I don't do that. That's going to mean I want the young to save. I want the young to save. If the young want to dissave, this isn't going to hang together. Okay. So the way the saving function is going to go, if you calculate the optimal saving function, it's beautiful. It looks like this. Looks like 1/2 W1 minus W2 PI plus 1 over PI. That's what the saving function looks like. With log preferences. So you save half your endowment today minus, see, you save less the bigger your endowment tomorrow, and the smaller and the bigger the rate of inflation is. Inflation is a savings killer in this model. So if I write down on my equilibrium condition now, this is beautiful. I write down M over PT. I've switched to T's. I don't know why I'm switching from I's to T's. But I'm going to do it. W1 minus W2 PT plus 1 over PT. And if I just multiply by PT and rearrange, I get this equation. If we do this right. This is interesting. And I want that equation to hold for t greater than or equal to 1. So this is it's beautiful about this. This is a linear first order difference equation. And we're going to be constructing, and we want to solve it. Boundary conditions. We have none. We have none. This was something Samuelson's article is focused on. So that means we're not going to have a unique solution. We're going to have more than one solution. So if I just analyze this equation using what we know about linear difference equations, I get an equivalent. I get a class of solutions that looks like this. And you check this out. For any c greater than or equal to 0. So c is going to be, it's going to be an object. It's a constant that indexes the continuum of equilibrium price paths, price level paths. So the price level is not unique. Okay, so if we stare at this, we've got our hands on all the price levels, and then once we know the price level, we can get the allocation pretty simply just by using what do we get? We get, let's go get the allocation. I know I'm going to solve, let's take this over here. I'm going to solve for CTI from this equation. And then the second equation, what's my second equation? So I'm just going to use the budget constraint, CII plus 1. What was that? That was equal to my endowment, which is second period endowment is W2. And then I have M over PI plus 1. That's my second period. That's my second period. Yeah, that'll work. That'll work. So that's how I solve for the endowment. For the consumption allocation. So I've computed an equilibrium. And for different C's, it's kind of a bad notation because that C, that means that's just a constant. I should have made it something else, some D. It's just a constant. The reason it's bad notation is we already have C for consumption. So put the D here. Okay. So I'm going to stop now after I ask you a question. How do these equilibria relate to the ones I said we were turning our back on the Gale diagram and the arrow times zero, arrow to brew times zero trading. I can't quite do it. To the ones we discovered with our Gale diagram. And I'll tell you, let me tell you how to think about that. I'll give you a way to start thinking about it. And then you think about it some more on your own. I'll do the easy one. I'll take one, set D equal to 0. Now, what does it mean? What does it mean to set it? We've defined a competitive equilibrium. We've committed ourselves to that. We've computed it, and when we were done, we found we did not have a unique equilibrium. There's a whole bunch of them. And we want to discuss what they mean later, but so when it says set here is, that just means, i.e., inspect one of the equilibria and kind of think about what's going on there. That's what that means. It's not that anybody is free to set this. And that fact kind of concerns Samuelson, and it's concerned other people. It concerns policymakers in various countries. Okay, I'm going to set it equal to 0, and I'm going to inspect that equilibrium. So what does that look like? Well, that looks like PT is equal to 2M over W1, 1 minus W2 over W1. That's a positive number. You have to check. This is a positive number, so this is a positive number, and it's constant. You see no t here. So that means pt plus 1 over pt is equal to alpha t is equal to 1, but that was equal to, I see I can't keep, arrow and the brew keep coming back into my head. So this was one of the equilibria. This is this was one of the equilibria in that Gale diagram. And if you notice, that was the high interest rate equilibrium. What was the high interest rate equilibrium? What we called it. The rate of return on currency was 1. There was no inflation and there was no deflation. Okay. So this is so much fun. Let me ask you this. Stare at this equation now, and let's take an equilibrium where D. That's what I want you to think about. When D is positive by some whatever amount, that when we're selecting an equilibrium, what do you think the limit in that equilibrium of alpha t equals pt plus 1 over pt is in that equilibrium? The limit of that as t goes to infinity equals what? Limit, I should say, equals the limit of t goes to infinity pt plus 1 over pt. What's that limit equal to? Question mark. If you're good with limits, you could see it from this equation. Because remember, W1 is greater than W2. So I want you to think about that, and then I want you to think about bringing that into contact with the Gale diagram. And that'll actually be fun, and it'll yield insights. And then you will really have your hands on the what's making Samuelson's model tick. I'm going to come back to one thing before I conclude this little section, this lecture. Let's stare at this equation. Because with Samuelson, we are imposing rational expectations in the sense that this price here, this is today's price level. That's tomorrow's price level. But it's playing a double role. It's what tomorrow's price level is actually going to be, but it's also, there's no randomness. It's what everybody thinks it's going to be tomorrow. So this is a forecast and of tomorrow's price. So, you know, and we're getting this from, so the price of the day depends on what people think it's going to be tomorrow. And, you know, they end up being, you know, they have to formulate their optimum problem. They have to have a view of what the price level is going to be tomorrow. That's where this came from. That's where they got their savings from. So that's where this came from. This came from their savings decision. Okay, so we stare at this equation, and we can sort of tell a story about it. Money is valued today because it's expected to be valued tomorrow. And it's going to be more highly valued today the more highly valued it is tomorrow. That's what this equation is telling us right here. Okay, and when and that's true in all the settings that we're talking about. When D is equal to 0, it's money is valued today at a level, and it's expected to be valued the same tomorrow. And that's associated with his D being 0. It's a common one. So this is a model where expectations about the future are influencing in a very heavy way what values are today. And I'll just it's a really good place to stop and to think about these ideas. Thanks.